No, no, you have one. എനിക്ക് എന്നെ കിട്ടാതിരിക്കില്ല ഒരിക്കലും. അങ്ങനെ ഒരു ഡൗട്ട് മുറുകി ആവില്ല.
Good afternoon, Dr. Thatcher, Dr. Herein, and Dr. Prabhakar. Good morning, Dr. Prabhakar. Good afternoon.
हाँ यशपाल बोलो. यशपाल, हेलो. यशपाल, हेलो. हाँ बोलो. ये 2:30 को यार हमारा सेशन चालू हो गया है, तो आप हाँ बोलो. नो प्रॉब्लम, नो प्रॉब्लम. क्या है ना कि तुम जो बोलते हो ना पूरा मतलब इट्स ऑल अवेलेबल टू द होल प्लेस, राइट? सो yeah, let us do the moderation and then we can give you a chance to speak. Okay, you understood na? Chalo, huh? Chalo. Yeah, is Aileen? Hi, can I hear? Hi Aileen, can you hear me? Are you there? Oh, she's just. Oh, wonderful, wonderful, wonderful. Do you want to address the people anyway? Oh my goodness! No. I'm so sorry. It's horrible time there, right? Please go back to sleep. Go back to sleep. Yeah. You take rest. You take rest. I guess it went on okay, right? I saw your message, so I guess it went. Yeah. All right. All right. Wonderful. Wonderful. All right. All right. So, Eileen, I take your leave. Then I'll go back to the hall. 2:30 it was supposed to start. These people have just gone for lunch, and we'll. Yeah. Okay. All right. All right. Bye bye. Thanks for the support. Thank you.
Let's start, I think. Let's start. 240 है 230 we had told them.
It was सर एक बार देख लो क्या
नहीं वो एक सेकंड में तेरे को बता रहा हूँ तुम्हारा कौन सा है. यार ये चौधरी देवीलाल यूनिवर्सिटी का एक यशपाल है, वो उसको लिंक दे दिया, गलती किया. क्या हो गया? वो यूं ही फोन करता है.
अयो अरे ताळे वेंडिंदा उन्नु दावड़ ताळे
Yeah, he will take a no, no, he will take a number of dinners from here. We take dinner now. Around 3 o'clock, I take a dinner. And that's how it's going to be done. Oh, it cannot be a free for all kind of a thing. That's right. Yeah. Right? And it shouldn't be not really covering it. I would expect that no, the third session is also going to be interaction. There is no discussion. There is nothing compulsory. That's why since we have a lot of kids, what happens is if you don't take these people, why should they be in this? They can go around, enjoy life outside. So why don't you people come up front? I don't want empty things. Come up front. Come. All those seniors, they're okay. If you're a undergrad or postgraduate student, I want you to come up front. Faculty and all, you can sit wherever you want. already 2:45. Let's start. We cannot. I don't think it's a good idea. So, what's the kind of strength that we have? Let me be a little negative here with a critical mind. I am a critical thinker. So, how many did we start off? We had a good population when we started off in the morning. Now, in the afternoon sessions that we gone down. Instead of the thing should not be, common. So, I don't know. You guys tell home that you're coming to a conference and then you don't attend the conference. We have to take attendance. That sounds good. We do that. We do that. Yeah. And now when I say that we take attendance, she reaches out to her phone, she's messaging her friends. That's what is happening. Right? Right? Yes? I'm a teacher. I know what you guys are up to. Let me know. Right? Huh? So, Prabhakar, second talk. Thank you. So we are starting about 15 plus minutes late. This is a session that focuses on the chemistry, the establishment, the experimental observation of the microphone. Sorry. We start a little late, so I'll stay in the frame so that you can get it. I request Mr. Prabhakar to, when the questions come, it's a good idea to have the later part. All right. Thank you so much. So, yes, the genesis of murburn concept is with heme enzyme peroxidase. I don't know. So I would always start off my talks with tribute to my Guruji. I worked in Lowell Hager's lab for 2 years in 1999-2000, and this work was almost done except for some parts which were done by Abhinav and Danny back in India. Much of it was done by me in Lowell Hager's lab. Lowell Hager was chair of Urbana-Champaign School of Chemistry, Department of Chemistry, for a good 25 years. Very loved professor. He was also a National Academy of Sciences member. And he was the pioneering scientist who discovered this enzyme called chloroperoxidase. We'll talk about that in extensive detail, but I had extensive debates with Lowell when I worked with in his lab, with him in his lab, and then I differed with the mechanistic aspects. So he was so gracious. I was getting the funding from him. I was staying in his lab. He allowed me to question his ideas. And that's what scientific spirit is about. It's about doubting, questioning, exploring, and aiming to answer. That's what science is about, right? So he was a senior. Lowell, my tribute to you.
my gratitude to you. As long as I live, I will keep your name flying high. So, yeah, that's Lowell Hager. So with that, ये बोला. Well, I joined Lowell after my first postdoc in France. Now, from now we have now the inaugural session is over. We have lost the non-specific people. We are mainly focused with the people who are interested in the core part. All right. So the content will be very focused, and ideally, I would expect questions at the end. But if it is a burning question, you cannot just go forward further. You can stop me then and there itself and ask. But preferably, it is better at the end. So the slides have question numbers. You can write down. That's why the pad is given. That's how it goes. So after my PhD, my master's was in Goa University. I did on keratinases, protease, and PhD work on lipases at IIT Madras and NIBH Japan. I went there for 1 year. So postdoc was in epoxide hydrolases in CNRS France, Marseille. Now, until then, my work, like what Sir Venugopal Sir said, basically my work was enzyme, substrate, their interaction, whether the lock and key theory or the Koshland's induced fit theory. It's basically a topological complementation of the enzyme with the substrate. So this is the same philosophy that even receptor ligand, all that biological interactions are fundamentally specific because of this topological complementarity. And then collision theory was yet another this thing. The more the collisions, the greater the reaction rate. So we are trying to understand biological phenomena here, and biological phenomena are better understood if you try to understand the founding chemico-physical principles. And I would request you to pay attention. You have come this far. It's not to talk amongst yourselves or share pleasantries. Please stay focused. If you are not focused, it takes away my attention and it spoils my day. So please stay focused. This is for the younger generation to get. All right. So, and then the transition state theory, like what Professor Venugopal said, the activation energy barrier is reduced. And then these are the basic theories that I considered, I learned, and I applied before I got to that lab, because I was classically dealing with all these enzymes. I was an enzymologist. So, but when I came to Lowell's lab in 1999, the world changed for me, completely changed, because here was an enzyme, a biotechnologist's dream. You could leave that enzyme puppy on the desk for days, hours. Nothing would happen to it. Have you seen any protein like that? No. But then this was one protein. It was very rugged. It was beautiful. So this protein looks like this, 42 kilodalton. Now you will have details. All right. I'll put more details. Things like that. This is how it used to look. You can see into it, and you can see the heme through the small aperture. So it's a globular protein, and here is the heme, the cofactor inside, and you have this is how it looks like, the ribbon, and this is the stick heme inside. So in physiological function, it basically produces an antibiotic called caldariomycin. So it's a haloperoxidase enzyme. The chlorine insertion is this enzyme's role. Now, so this is a very versatile enzyme, and it is responsible for the production of, I would expect you to write down any notes or anything. Please pay attention. Just put your heart into this. Don't write any notes. All this is available here. What is important is you see me, learn to see my vibes, meet my eye, try to see what a genuine pursuit feels like. And if you believe that you can also do it, that's what it is for. There's no need to write down any notes. If you have a doubt, that you write down. Otherwise, let it be a smooth ride. All right. So now this was a protein, and this is its function. This molecule is its function. This is the essential cofactor. This is the kind of look that it has. The reactions that it contains, because it catalyzes. That's what we are very interested in, basically. So basically, it uses a peroxide, and it can dismutate peroxide to give oxygen. Then it can take an electron-rich amine like this, or a phenol or something like that, and it can strip one electron of it. And then it can insert oxygen atom into alkenes, sulfides, or even benzylic hydroxylations. It can catalyze. And then it can also insert chlorine atoms into molecules. Here it is a chlorohydrin formation, so in presence of chloride ion. So this is the reaction assay that was being done in the lab. It was somewhat similar to the natural substrate. This is monochlorodiamidone, and it was getting chlorinated in presence of peroxide and halide, which is Cl minus. You would get chlorination assay. This was the scenario under which in 1999 I went to Lowell Hager's lab. All right. So for me, it was quite intriguing how all these four reactions, which are very different: peroxide dismutation, electron abstraction, oxygen insertion, chlorine transfer, all these four reactions occurred. The classical theory said that it occurs at the enzyme active site. One active site, one intermediate. This is the intermediate. Now you will get some details. Dayanidhi, you said you wanted to attend this symposium, right? Where were you? Sit. That boy asked for opportunity. He took so much of my time. He did not register. He spent that time. And now this is what is happening. Now, when you get an opportunity, you make use of the opportunity. It's not every day that something like this will come around. I'm telling you, you don't get a person's negative attention. You try to get a person's positive attention. Please that. And I should not be, this is something that is going to be streamlined. This is going to be documented. I know it fully well. But my passion is directed at those people who chose to come here. So now here you see the active site is like this. So the peroxide comes in, creates this active species, and then the chloride ion comes at the active center, and then the substrate also interacts at the active site to give the chlorine atom transfer. So completely, whether it is an electron abstraction, it has to come into the active site, and the electron gets abstracted from there. Whether it is oxygen insertion, all this, the oxygen gets inserted here. So the chemistry is all this reactive species formed at the active center, and peroxide was supposed to be highly reactive and inactivating the enzyme. Because after some time, when you put the peroxide into the reaction, after some time, they saw that the enzyme stopped to work. There was no further reaction. So they thought that the enzyme got deactivated because of the oxidation effect of the peroxide. All right. So these were the prevalent ideas that existed in the lab and in the world, because this was the leading lab in the world. He had discovered this enzyme. He had proposed the mechanism. He was a National Academy of Sciences member, and he was the, basically the mouthpiece of what the world believed in as far as chloroperoxidase is concerned. Now, this is very important enzyme because it is responsible for more than 90% of the naturally occurring halogenics, right? So oxygen peroxide, everything was occurring at the active site. So there was, however, a slightly marginalized view that hypochlorous acid or hypochlorite was produced from inside, and that also could mediate chlorination. So now, first thing what I did was, when I went there, some of you would go for projects, PhDs, masters, postdocs. So when you go there, you will get a project to run. So now please bear with me, professors. My talk would be primarily directed towards the main audience. So please bear with me. So you would get some projects to do. The projects will have a mandate, and you would be getting some funding or something, and you will be expected to do that work. my project was an NIH project, and then National Navy project also. So in that, my mandate was to ensure a good reaction where this peroxide, the inactivation by peroxide was supposed to be, we were trying to make mutants of the enzymes and things like that, so that we could this enzyme is a biotechnology specialist, because you see these oxygen insertion reactions, we could make chiral synthons. Multiple JACS papers were published wherein, because the oxygen insertion occurs inside, the enantioselective products were formed. So epoxides are very important chiral synthons. So now my mandate was to see how, if the reaction needs to proceed, we needed peroxide, and peroxide was also inhibiting. So how do I get over this on a application scale? That was my role in the lab. Now I found that, okay, when I did some classical approach, first step in the procedure, explore. See, I have got 3 cardinal principles. Listen to this. Explore, resolve, prioritize. Chance favors the prepared mind. Pursuit of excellence is based on what you have and what you know. These 3 things you will see me repeating again and again. And these 3 principles, if you repeat in your life, put it through a loop, you will generally come out in a right direction. So here, before I go around trying to exactly solve the problem, I try to explore a bit. First thing I did is I took peroxide, then methyl hydroperoxide, ethyl hydroperoxide, and as expected, peroxide, small molecule, it can go into the active site. Well, boom, higher rates, methyl peroxide, and then as the molecule size increases, the rates go down. So this is the active site mechanism. Fantastic. But one thing I saw was that this enzyme could actually turn over millions of peroxide molecules before it got deactivated. So the idea prevailing in the world was the enzyme gets deactivated by peroxide, but it could convert. Here is the reaction. You could, at micromolar to nanomolar, you could get thousands and millions of molecules converted. So turnover numbers, that is called. Now, then I saw that, see, here is data. Now, this is the theory, here is the data. Now, if you remember my earlier slide, there will be some theory. You are supposed to map the theory with respect to the experimental observations, right? So here is the experimental way. What do? You have got phenyl ethyl sulfide here, and you have got styrene or some molecule like that. I think it is styrene, yeah. So you are monitoring the disappearance of the substrate with various peroxides, and here is the reaction. After some time, it stops. So they thought that this is because the enzyme got denatured. Now, one simple thing I did, I added more peroxide. One simple curiosity. What will happen if it's deactivated? Let me add some more in that peroxide. Boom, the reaction goes again. I added, after some time it stopped. I just add more peroxide. The reaction goes on. So the basic thing was, it was not peroxide getting to deactivate the enzyme. Peroxide was just getting depleted. That was one. Leading lab, such a major perception with one curiosity, one exploration changed. It changed my mindset then and there. That is, there could be n number of beliefs prevailing. Unless until you ascertain yourself, you don't need to reinvent the wheel. You don't need to touch 20,000 volt line and say that, okay, I'd get killed. But there are certain things that you can physically verify, particularly if you are going to be working on that project. You want to verify that the observations that people take for granted are in fact placed well. So here, both in the sulfide oxygen insertion and alkene epoxidation, both the same thing happened. Only thing is that sulfide oxidation was faster because it's more facile. So the next one was that I chose to study the one electron abstraction. So I studied the oxygen insertion reaction, the peroxide utilization reaction, and here I am studying the electron abstraction. So what I did is diverse type of molecules. It's a heterocyclic amine, and this is a classical peroxidation substrate. This is a phenylenediamine, tetramethylphenylenediamine. This is phenolics. So diverse substrates and different stoichiometries reactions I chose. So I probed the one electron abstraction reaction mechanism, and I saw that in the peroxidation reaction, somehow the alkyl hydroperoxide was better than the aqueous peroxide, that is the hydrogen peroxide. And unlike the classical enzymes, this had different pH profile. Usually, you have a pH profile like this. You draw the activity versus pH. You would have generally a bell-shaped curve, wherein this will be the optimum. But here you see, for different substrates for the same one electron abstraction reaction, for ABTS, for guaiacol, for pyrogalol, for TMPD, the profile, they had multiple maxima, they had multiple pH ranges. So it's not the kind of data that I was getting was not really one active enzyme species doing one mechanism at one active site. It was not really translating to that. It was not speaking like that. So there were multiple mechanism differences in contrasting to oxygen dismutations or oxygen insertions. Organic peroxide being more efficient, pH profiles showing, TMPD showing 2 peaks, and this suggests that there was some mechanistic difference. Yet again, one aspect was this one electron abstraction. This is a terminal olefin. See, it's an allyl benzene, it's a molecule. Lowell's group had seen that this is the native chloroperoxidase, the enzyme. It's just like myoglobin, hemoglobin, it's red. Okay. Now, this thing becomes green when you put in presence of peroxide and allyl benzene. Why? Because this heme was giving a mechanism-based inactivation conjugated in a covalent derivatization product because of this molecule, and it was becoming green. So what I try to probe is, does the electron transfer reaction occur at the active site center as they believed? What I did is, I took a phenolic like this with just a hydrocarbon substitution and F-terminal allyl substitution, that one. So you see, the rates are almost identical. So basically, if it was occurring at the active site, I would expect inhibition for this, but it was not. And also, the active site excluded molecule like such as this, it was also getting converted. So you see, the CPO active site is very small. This is it. So this molecule would completely will not get into that. So these things also said that the reaction might not be occurring there. See, what are we trying to understand when you understand a phenomena? A phenomena is something that changes in time. You want to understand the space, mass, all that flux. That's what I was trying to understand here. What happens in real time? Okay. Now, here is another thing that I did. What I did is diethyl pyrocarbonate. It's a derivatization agent for histidine. Now, if you see this protein, it has histidine here. All right, in the active site, it has a histidine, it has a glutamate, it has a distal cysteine here. So this diethyl pyrocarbonate is a sensitive agent for histidine. So it makes this kind of a molecule. So derivatization. Now, if this was catalytic in the active site, then I should get inhibition. So when I did that and try to monitor the reaction progress in time, you see that for epoxidation and dismutation, the fall was pretty drastic within 30 minutes, whereas the peroxidation reaction, that is the one electron abstraction reaction, it was practically constant for the same derivatization time. So clearly, the one electron abstraction reaction and the oxygen insertion reaction, they were different. 1 electron and 2 electron were proceeding at different mechanism place. And in this one electron reaction, this is actually Danny has worked on this. I think I'll continue to speak just for, I thought Danny will speak, but then what happened here is yet another interesting phenomenon. This is something that has changed man's perception in a big time. One single simple experiment. Like what peroxide, that inhibition or deactivation gave me the confidence to challenge established norms. This was one night I was just trying to do the reaction. The reaction had nothing. Enzyme, ABTS, the one electron rich substrate, and peroxide. So you have one reaction. Now what is being done? So ABTS plus H2O2. No reaction. Okay. So ABTS plus H2O2 plus enzyme X-rate reaction, right? Or product formation. Okay. Form. At the rate is say Y. If I put X, it might also signify no reaction. That's why I've gone to Y. So ABTS plus H2O2 plus enzyme plus azide. This is what I was trying. Now, yeah, that would be nice. Azide, if I had azide. So azide is a classical inhibitor of heme enzymes because azide binds to heme iron. That's known. So before I went to that lab, azide was used to stop enzyme reaction. Yes, thank you. That is wonderful. So you put it here, the pocket. Yeah. Now that gives me mobility. Thank you so much. Now, you see, before I went to the lab, azide was used to stop the reaction. And because what happens is, there is the enzyme active site, there is a heme, right? Fe, it's supposed to bind N3 like this. This is the same mechanism for cyanide. Yes. All right. So now this was used to stop the reaction. Now what I was just exploring, and as usual, the if you can you understand the plot here? It is negative logarithm of azide. That is, here it is nanomolar, here it is millimolar, right? Here it is millimolar, nanomolar concentration of azide. So you see the activity. Can you make something out? What is happening there? Now, if I take, say, 10 millimolar or 100 millimolar azide, no reaction. Okay? So that we explain it with this, there is no access and the enzyme stops. But ABTS plus H2O2 plus enzyme plus N3 minus, but at say 1 micromolar or 10 micromolar, I get say 2x or 3x reaction. The same thing that was inhibitor was enhancing the reaction multiple folds. I saw it, I said, did I do something wrong? I read it. I was getting the same thing again. And I reported to my PI, Lowell, I'm getting something interesting. Lowell said, artifact, some artifact. I said, how can it be an artifact? I'm getting it reproducible. Then he said, it might not be that important. But for me, this thing, this single observation, pursuit of that observation is going to increase your offspring's lifetimes, going to find solutions for great many maladies like cancer, aging, neurological disorder and all that. One single observation, pursuit of that. So I am stressing on this because, one second, sir, one second, my flow. I just want to go one flow. This single, more than the papers, more than the recognitions and all that, each one of you will be doing some science. You will get to see something interesting or something important. If you try to place it always with respect to what you already know and don't allow your curiosity to tickle your fancy, your imagination, then you are not being a scientist. Don't do science if you want to do that. I am here. All this is here only because of this simple. I did not buy it. I loved Lowell. He was everything to me, but I did not buy it. I did not buy it. I didn't think it was merely an artifact because it was reproducible, and it psychs a person. The same thing at higher concentration, it stops. At lower concentration, you see, this is the normal without the control. The control is here. With azide, at a particular concentration, it is going. Why should it show such a variation with respect to concentration of this? And then it is not just for ABTS only, it is also for multiple other substrates. And that is not only for chloroperoxidase, horseradish peroxidase, and also other for substrates. And in pH, this whole thing varies. So it is not necessarily the one electron reaction is not something that is occurring at the active site. It is a more complex phenomena. And the explanation to this was that it occurs at the binding site. So we know how to probe that. Yes.
This is the basics of the homeopathy.
Yeah, I will come to that. Yeah. We'll come to that. We'll come to that. Please, Unath Katji, 1 minute. Now, here I am trying to correlate this experimental observation to the theory here. How do we probe the theory? Now, we know that heme, the Sore, this is the signature of UV signature of heme. So, now you have, this is pure chloroperoxidase. Now, you have excess, about 20 millimolar azide, you have this. So, 10,000 times excess, you have binding. So, the Sore, when it is bound to azide, that signal is this. But even in presence of 1 or 2 micromolar, CPO, chloroperoxidase, and I have 200 micromolar, 100 times excess of azide, practically very little of the population has changed. So, at this kind of concentration, there is no binding whatsoever. There is no binding of azide here. I mean, very insignificant level of binding. This is not because of binding. And very clearly, this unusual dose response. Here is what we are talking about. This is dose response. We are changing the dose. This is low dose. This is high dose, low dose. So, this is something called hormesis. Danny will talk about it in great detail tomorrow. We will come to that. Alright, so homeopathy also talks about this. That's what you are coming to, right? So we'll deal with that. So the point is we are coming to it at great length. What here I was trying to stress is how a simple observation is translated or correlated. It stimulates your thought process, and how you vis-a-vis correlate it with the known theory and try to say, no, this is not that mechanism. All right. So next slide is the cyanide. Now here is an inhibition effect. That was an activation effect. Now here is inhibition effect. Now cyanide also binds here. This is Abhinav Parashar's wonderful work, his thesis work. Sadly, his thesis, Danny's thesis got approved pretty easily. Abhinav's thesis, it went to the people who were from Andrew Munro and all those people, I'm putting his name very clearly on record, because he kept a person's valid work for almost how many years? 2 years, 2.5 years. And he gave us big lectures that, we are all, Brits think that they are the only people who can do science. Yeah. All right. So here, you see here, cyanide. Now, see what happens is, here you have activity here the scale is different. Here it's a positive scale. So the concentration of cyanide is logarithmically increasing on the x-axis. So as the cyanide concentration goes up, you get increasing. So with this you can calculate an equation called IC50, inhibition concentration cyanide, where you get 50% of maximal activity. So that is IC50. You see, the classical theory is that like this, as cyanide also binds heme as CN, sorry, C minus, yes, CN minus. So this CN minus, that is facilitated at alkaline pH. The pKa of cyanide is around 9. So if you are doing biology, please understand some chemistry. Without understanding chemistry, if you try to do biology, biotechnologists, you call yourself biotechnologist. Many of my students, most of my audience is biotechnology students. So don't run away. When I was doing my master's, I was writing an exam, biochemistry exam. I'm taking some time out to give these messages, because that is what when you come here, that's what it is for. I was writing my master's exam, and I wrote my biochemistry exam. 2 hours into the exam, I cried. Actually, I had beard and all that. I was almost 21 years old. I cried, tore my answer sheet, and ran away from the exam hall. And Sanjeev Gadi, my lecturer, he said, "Murali, why did you had done well. You had almost, aced actually compared to others, and you had done well." I said, "No, Sanjeev, I didn't understand what I was doing. Mugging some cycles, some chemical structures and all that without really understanding the rationale." It was a bomb planted in my head by Narasimhan sir, my 8th class mathematics teacher. I realized when I probed my head. What had happened was, in 8th class, half-yearly exam, he had given away the maths answer sheets, and he had kept one answer sheet with him. PG Sri Raman, my Sanskrit son, as usual, was highest, 94 marks he had got. I had got 85 or something like that. I had got more. But Krishnadas has got only 76. Narasimhan sir said he kept his answer sheet, no extra twine, nothing. I still remember that very vividly. That one single, only the main answer sheet, no extra supplement. PG Sri Raman had all that. So mine also had. So Krishnadas, I still remember his handwriting and all that. Narasimhan sir raised his answer sheet and said, "This boy, he has only 76, but I liked his answer sheet more. I liked his work better. Because he knows what he knows, and he knows how to differentiate it from what he doesn't know. He has done what he knows, and he knows that all other things he doesn't know." And that thing was very fundamental. Now, all of you cannot be toppers in your class, right? But then you will have to take a subject. You become experts in that. You know what you do. That is what you can be. All right, that is the message. And when I did my master's, I was writing biochemistry without really understanding the mechanistic principles. Why do certain things happen? Why can't this react with that? All those things I did not understand. So that day was a changing point in my life. And from that day, I became more curious, more conscious, more aware of my role as a scientist. And some of you are teachers, some of your students. When you do interact with your students or teachers, don't settle for, diluting your own agenda. When and if possible, say something positive and try to follow through. That's what makes you different. That's what makes you unique. That's what proceeds. That's what, enhances humankind. Otherwise, you're just being at, low level, at a lower level. That is not what you're getting trained for. So here, what you see is all that digression was, I have already said 10-15 minutes of data and science and all that. Now I need to put some personal tidbits so that I can get your attention back. Did I catch your attention? Good. So now let's come back to cyanide and chloroperoxidase. Right now, here the cyanide is supposed to bind here at alkaline pH. Now I want you to be a little careful about the data. Now you see here, pH 9 IC50 is 1.4 micromolar, pH 7 is 461 micromolar. Some of you will do some project, sir will say, you produce data, you will take the data and go. what does the data give? It gives you some idea about the reaction, and that's what you're supposed to do, think about as a scientist. Now, if cyanide binds at the active site center, and if it is through a negative ion, pKa is 9 of HCN. So does this abide by the active site theory? Can you say, does it abide by? pH 9 have lower IC50. Is it good with the active site theory? No, it is. It is, because pH 9, alkaline pH, so it will bind effectively. So good. So this is good with the active site theory. Now you see, let's take another substrate. Let's say 8.9 pH for HRP pyrogalal. This is HRP ABTS. This is HRP pyrogalal. I get IC50 is around 171 micromolar. 9.2, 21 micromolar. Does it agree with the active site theory? Yes, it does. Because once again, alkaline pH is giving a lower IC50, alkaline acidic. Now, but then you explore a little further. You come here to this, compare this and this, this and this. You have to make global sense. You don't want to make local sense. You want to make global sense of your data. Now you compare that. Now you see, here is HRP ABTS at pH 5. 1 millimolar ABTS, 0.2 millimolar. I get exactly almost the same profile. Now you compare that with pyrogalol and pH 5. Do you see something here unusual? At 0.2 millimolar, I get IC50, 44 micromolar. At 2 millimolar, I get IC50, 10 micromolar. Does this agree with active site? Higher concentration of the substrate, I get lower. How is that possible? And then you compare now this with this, this with this, things like that. pH 5, you see what is the IC50? At 2, it is around 10. At 9.2, what is it? 21. Which one is lower? pH 5 is lower. So does it agree? No. So it doesn't really agree. You can say, remember that ant, you can take some points, that circle will look all nice, but you try to take points in all the global space, it is not agreeing. Similarly, you see this and that and all that, none of these data will agree, make global sense. So that's what a systematic exploration done by Abhinav. He showed that the cyanide inhibition is not actually, and even otherwise the data points are not actually fitting. There are some beautiful looking fits, but then some data points are not really going there. Some places they go above, like we showed in Azai. So the point is that here you see 193, this is pH 5. pH 5, here see 193, 461. Yeah, you want to go? Yeah, please, no problem. And here you see, nice. Thank you for coming. Sir, thank you. Come. All right. So here is another quite an important phenomenon. Here you see HRP plus ABTS reaction. This is there. Here you just add HRP plus H2O2. H2O2 we know is consumed at the active site, right? But then you see ABTS, a product that can, a substrate that cannot go into the active site. It is given, and boom, peroxide gets consumed. So the oxygen or peroxide consumption, the redox activity, can be affected by the presence of a non-active site included substrate. Did you understand? This is called the thermodynamic pull, the sinking of electrons by the presence of substrate. So it shows that it's an interactive equilibrium that is at work. Yes, anybody wanted to ask something here? I'd prefer the question at the end. We'll take the question at the end. So now we saw oxygen insertion, peroxide dismutation, We saw one electron abstraction. Now we are coming to chlorine transfer. Now chloride is given as an ion. Now in the respiration, what happens in respiration? ADP has to be attached to phosphate. So chloride is an ion just like phosphate ion. Do you agree? Cyanide is an ion, azide is an ion, phosphate is an ion. Now you have to make sense from here and there. So that's why I'm saying you have to know some chemistry. So now I have to be in this. I feel like getting more close to you, but then I have to keep this recording this for posterity also, so that it can get recorded. So the chloride ion transfer, when I went to the lab, it was supposed to be primarily an active site theory prevailing. Why? Because low rates by diffusible species, when you react it with chlorinating speech like bleach, you get lower rates than you get with enzymes. Then if you give, say, now substrate A and B, A plus B to chlorination mixture, you get only A converted. So that kind of, if it is a diffusible species, you would have both A and B converted, because there is no selectivity. But then how can, in the enzymatic reaction, if it is via a diffusible species, there was only a few people who said it was by a diffusible species, then how can it be selective? This is very important. Whatever you are going to study in the next 2 days is based on this simple system. This is one enzyme, one activation system, one substrate. One enzyme activation is peroxide, one substrate is whatever molecule you give. It's a simple system. The respiration system, photosynthesis system, vision, all that are complex protein systems. Now I am trying to tell you the fundamental of these mechanisms by one enzyme system. Okay, so here rates difference between substrates, then synthetic analogs. Wolfgang, one Swiss researcher, made and said that it was at the active site. Then Michaelis-Menten kinetics were reported in some Nature journal. Okay, and then structure elucidation of compound 1. Compound 1, the intermediate, was also structurally elucidated with electron paramagnetic resonance. These are all sophisticated techniques. Once an idea gets set up, there will be sophisticated instrumentations. All those kind of paper will get published in big time journals. All right, that is not great science. What is great science? Great science is not to catch the nose like this, but you can as well do it like this. Simple definitions, simple things, simple ideas are also good science. It doesn't mean that sophisticated instrumentations are bad science, but what I'm saying is not everybody can get access to sophisticated things. So now when I went there, the lab was, now once again we have gotten some 10-15 minutes, so I'm coming to some personal tidbits again now. Now when I went there, the lab was, he was a big guy, he had huge lab, and there were chemicals lying around all over the place. So I said, I hate wasting. I like to channelize resources. I like to optimally use resources. So what I did is, I said, let's get all these classified, let's document it, what chemical, where, all that. He said, is that necessary? Yes, I wanted to do it. Otherwise, we have so many things. I might order something that we already have. That's not good. So I spent almost 3 months cataloging all the chemicals we had in the lab over 20-25 years. Now what that did is, I could find so many chemicals that I could use for my experiments. So since my master's was in chemistry department, my master's was in biotechnology, my registration at IIT Madras was in chemistry department, my coursework was in chemical engineering, I could get a little bit of chemistry, I could get a little bit of engineering aspects, process, reaction, all that, and I could put 2 and 2 together. So all of you who think that I will do biotechnologist, I'll do biotechnology, I'll just know how to put one restriction endonuclease cut and do the incubation, that's my biotechnology. Sorry, that doesn't work. You will have to be willing to learn a number of things. So, and you will have to be involved in the lab activities, and I gained Lowell's respect because of that. He saw me meticulously cataloging and all that, so I did not order any further chemicals. I I talked to Lowell, I said, Lowell, I'm going to leave scientific research because I want to go back to my country and do social work. Social work because one of my friends, when we were doing PhD at IIT Madras, he died, and I tried to get his birth certificate, and they were asking for some bribes, and I got very upset. I said, 22, 23-year-old guy has died. Why are they asking bribes? And I wanted to come back to India and do social work. So I told Lowell that I wanted to do research on my own, and this ability to do some things rather selflessly and independently gained my PI's respect, and he allowed me to explore things on my own besides doing the agenda of his grant giving projects. Did you understand? So what I'm saying is, if you seize initiative, if you are original, if you are genuine, if you are passionately involved in what you do, you will see your seniors supporting you also. Of course, they have to be of a good nature also. Okay. So I was lucky. I had that good fortune of working with him. So here, what I did is, having gained that kind of a background, I used diverse topography, dimensions, molecularities, all that. Sulfur lone pairs, beta diketones, olefins, all that. Some of you might not understand this, but what I'm saying is, these are the different molecules that can be used for chlorination. Now, all these molecules, when you try to understand a reaction mechanism, you want to understand how does the molecule get converted at the active site, or how is the reaction. So how will you collect data for that? So this is the way. I did see all those, and I could do simple spectrophotometric assays. Now, for some of you, for doing those, how does a product get transformed and all that, you'll have to do product assays, substrate assays, and I could do simple UV-vis assays with which I could get, and I could see that a diverse array of molecules could easily get converted with high rates, comparable rates, whereas these rates were basically size independent, and basically in 10 to the power 2 kind of ranges per second, pseudo first order rates, whereas oxygen insertion and dismutation reactions are site dependent, as you will see here. The same molecule, indene, it can be epoxidized and chlorinated. The same molecule can be sulfoxidized, and sulfinyl chloride can be made. So when I try to do the epoxidation reaction, I need much higher enzyme concentration. When I do the chlorination reaction, I need much lower. So in the chlorination reaction, also the reaction was not dependent upon the substrate concentration. You see, practically zeroth order. You know what zeroth order is? It is not dependent on the concentration of that substrate. So, but when you see epoxidation, the same molecule, and you needed a higher enzyme amount. So these reactions of oxygen insertion, they occurred in the active site, whereas these reactions, they did not occur in the active site. That is clearly indicated here. So oxygen insertion is at the active site, whereas chlorine atom transfer is not. All right. So that is shown by this. And very importantly, I told you that from a mixture, I chose molecules like phenyl sulfide, dibenzoyl methane. These could be traced. So these are finding ways to explore your ideas. What will happen if I take a molecule that is bigger than the active site and which is not soluble? So I should know how I can track it, how I can choose those molecules. That is how you will devise your experiments. All these things you have to know. And that's how I did it. So I found that even molecules that exceeded the active site and they were insoluble, that also underwent the selectivity thing. That is, I mix equal quantity of this and this. The reaction first consumed this and then only went for this. That's what this data shows. Now, how can a molecule that does not go into the active site and is insoluble also get selectively consumed? But then if you put the soluble intermediate and try to do the reaction, you will get 50-50 conversion. But in the enzyme, if it is through a diffusible species, how can I get selective reaction? So how I did it is, I showed that, have you heard of some idea called sustained release? Yes, sustained release. That is one by one, not at a pum like that. Now what I did is, now this is thiourea, okay? This is monochlorodiamidone. This is a sulfur containing electron rich molecule. This is a beta diketone with an activated carbon here. So now this is the signature of the thiourea molecularity, and this is the signature of the diketone signature. This is the UE with signature here. So if I added, say, if I took 100 molecule of thiourea plus 100 molecule of monochlorodiamidone and gave 100 molecule of HOCl, I would get 50 of this and 50 of this converted. That is what it shows. Or you understand, see, first when I give, quickly when I add, I get conversion of both. But when I add slowly, I get conversion of only thiourea. Did you understand this? This is a very important experiment that established murburn concept. Did you understand this? Did you understand? No? You did not. Please, I will tell you again. Now, here what is shown is, on the topmost, you see this thiourea signature, left side. Right side is the monochlorodiamidone peak. Now, if fast I add a large amount, like 50 it gets converted, almost something like that, high amount. But if I add the same hypochlorite bleach, slowly, small amounts, I get almost conversion of only thiourea, very little of. So that is how, so slowly when the same diffusible reactive species is produced in low amounts, I get the reaction to be highly selective from a mixture. So now if I come into this room, and if I see, say, if I see Muthu sitting at the end, and if there are not too many people here, I like Muthu, I'll go to Muthu, say, like that. But if there are too many other people here, too many Muralis, there will be too many random collisions, and they have a greater probability to be reacting and giving products. So thiourea is actually inherently more reactive than that one. So the enzyme reaction always gives greater preference for thiourea. So never does the enzyme reaction prefer the other molecule before this. So what I explored is, I explored multiple, on the right you see there, multiple reaction systems, thiourea MCD, thiourea indene, like that. In all the reactions, whatever the diffusible reactive species was preferring, the same was the preference for enzyme. That is something interesting, isn't it? And then the preference of the enzyme system could be modulated by changing the ion concentration, pH, and all that. How much preference? So there was something that was getting produced by the diffusible species, then, and that could be modulated by specificity, and selectivity could be modulated by just changing the reaction milieu conditions. So here, basically, sustained in situ generated species are capable of ensuring selectivity, and interactive equilibrium in the milieu determines selectivity. That's what is conclusively established here. Now, this, sorry, my bad, I'm so sorry. So, with that, I have shown that even a diffusible species can give, and here you see another piece of very important bit of data. The diffusible species concentration is more important than the substrate. Substrate is practically zeroth order, but this is practically almost perpendicular. So here I studied the mechanistic aspects of it. I'm not going into details because this is hardcore chemistry. This is called Hammett plot. So the linear free energy relationship. Basically, if you try to see the enzyme reaction, it's practically not depending upon the electron density. It's giving a zero. But the reaction with, say, a species like chlorine oxide or dichlorine oxide or chlorine or HClO, all that, you don't get that kind of straight slope and the rate actually is low. But then what I showed is you increase the halide ion concentration and you increase the pH and all that, change it, the slope goes flat and the rate goes up. So you can get that reaction to approach the enzyme activity. So basically that is the thing. So the application of that was, before I went there, I showed you the monochlorodiamidone was the substrate sold by Sigma for assaying chloroperoxidase. I just chose thionin, which is a colored agent. Very easily, beautifully you can do. This was published in Analytical Biochemistry. And the chlorination reaction, once again, I chose a molecule that is much bigger than the active site, and I could get the reaction occurring in the active site, outside the active site. So with that, we come to the basic overall outcome. So there's something called, when you study enzymes, there is an overall mechanism, there is a kinetic schema, and then there is stoichiometry. So stoichiometry explains the ratio of reactants and products. Here it shows that inhibition and activation can also be going through alternate product formations and all that. So it's not just one reaction that is happening. There are multiple interactive schemes wherein additives and all that can interact. That is what is shown here. So don't get worried when you see so many cycles, all that. Basically, so chloroperoxidase was the first murzyme. All right, that classical perception, everything was at the compound 1 active site. Cyanide binds at the active site, azide binds at active site. Here I showed that in the reaction conditions, there's something that is produced here, and that comes into and then gets into equilibriums with various ions, and then radicals are produced, and then that can also do catalysis. So this is the basic outcome. So that is where this idea of murburn concept comes in. Basically, classical, I am not saying classical enzymes are not existent. I'm just extending the domain of enzymology. What I say is there is there are enzymes that undergo primarily 2 electron reactions or group transfers are primarily here, and the electron transfers are supposed to be active only like this. But I say electron transfers are not something like that. It can go through diffusible reactive species, and some enzymes can go through diffusible reactive species. They may or may not incur topological binding. So this is a very, 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 very simple, subtle difference. Very subtle difference. Very subtle difference. As Professor Venugopal. One electron difference and the involvement of the diffusible reactive species. The diffusible reactive species allows effective charge separation. That's the role of oxygen. That's what I'm saying. So murzymes are extension of classical enzymes. Murburn concept is like what Professor Prasad Burra asked. The origin is mured burning, closed and molecule unbound ion radical interactives, and then mild unrestricted redox catalysis. And of course, the originator also gets to have a say, right? Murali's name should also go down. I'll not be here anymore after a few years, but the idea should go on. That's something scientists have, right? Scientists should have a very strong ego. Yes or not? Yes, scientists should have a strong ego, because unless and until you know what you're doing, what you're seeing, what you're hearing, and you believe, Benjamin Franklin said, you should be present in what you're doing and you should be very conscious of what you're doing. If you're adding a chemical, you forgot, did I add? Did I not? Gone. That set of experiment, gone. You can toss it out, because once you have that doubt, gone case. You have to be very confident of what you hear, what you see, what you think, how you calculate, all that. Small things. If you see Satyam Jayatu's logo, it is 1 plus 1 is equal to 2. 2 into 2 is equal to 4. Small things build to bigger things. Alright, Satyam Jayetu is my trust, my logo, all that. It means may let the truth prevail. The ego is very important. The ego is like knife. You can do good things with it, bad things with it. Right? But you cannot kill your ego. If you kill your ego, nah. That's what drives you. That's your dynamo. Alright? So, scientists are confident people. Scientists are argumentative. Scientists are not necessarily always amicable. So, don't try to please everyone out there. Have your individual opinion. Try to ask doubts. That's very important. If you don't understand something, don't nod your head and say you understood. If you do that, I mean, it's a disservice. So, here, once again, I'm coming back. You'll see me after every 10-15 minutes, I'll go a little bit, add some personal things, and then come back. Because an average person's, attention span is about 10 to 15 minutes. So I know. And personal stories, you will all appreciate because that's what is more interesting. Okay, so here is what is happening here is effective charge separation. And that's a random thing, a chaotic thing. And oxygen cannot be tied or bogged at one end. It is not a dog on a leash. You cannot tie it. It's a molecule free to go around wherever it wants. Yes or no? Yeah. So here we have the classical. I'm not saying this is wrong. Please don't get it wrong. I'm saying this is the classical mechanism wherein enzyme and protein, they have topography. It is very deterministic. So known inhibitor, the substrate binds. Beautiful. So, but when that inhibitor binds at the same site, this is competitive active site inhibition. It binds at a different site and changes the active site. It's a allosteric inhibition. So, enhanced formation, there is some kind of modulation, something like that. So, here you can explain high substrate selectivity, specific redox partnering, and integral stoichiometry. What is integral stoichiometry? 1A reacts with 2B to give 2C, or 1A reacts with 1B to give 1C, something like that. 1, 1, 1. But here you see what happens. The stochastic paradigm has a reactive species coming out or being taken in. It can be both ways. Murzymes can be, they can use ROS, they can give ROS, they can equilibrate with ROS, or they can modify one ROS to another type. So there are different types of murzymes which we are all trying to now predict and try to classify. That will slowly come to you. Okay. So what does murzyme do? Murzyme does, it can explain, that concept can explain broad substrate ranges, how different kinds of molecule, because once the molecule has come out or is attacking something bound here, you have multiple ways of explaining things. So here, non-specific redox partnering, non-integral stoichiometry, all that can be explained. So if you have 4 substrates, A, B, C, and D, to select one is from those is one. Specificity to attack at one, we'll call it at one locus. That is specificity. Omega or para, something like that. It's specific. A, B, C, D, one is selective. So basically, now I'm coming back. So this talk will be somewhat spiral. Whatever Laurent has said, we'll revisit. So in an enzyme reaction mixture, enzyme, substrate, so this O2 and H2O have gone here and there. The O2 was here, H2O was here, sorry. So there can be interactive equilibrium like this, out of which there can be a whirlpool kind of thing, out of which product can go here and there, right? So that's the kind of C. You have to see it different. So there is an interactive equilibrium. You cannot prevent some equilibriums. Once you mix, it's a pot. It can spontaneously react. Why should it not react? Our body, each cell is a pot. So that's what I've come to. It's coming to 4 o'clock. So now you will have your tea and all. Before that, you don't want it. So I mean, 1.5 hours is good amount of time. So I thought I'll break it here. So like that, now I'll come to the story part. So I told you that Lowell and we did not agree. So it's going outside the active site. He is a National Academy of Sciences member. The whole thing, he cannot put his name to that. He did not agree. So I tried to publish it, that work. Talk about it. You try to publish something which the seniors don't buy. My goodness, I had a tough time. Nobody was publishing it. So I was running pillar to post. The data was solid. But ultimately in 2006, without Lowell, I could get it published in BBA, Biochemica, Biophysica, Acta. So here are the number of citations here. See here. Now here, all these papers are in mainstream journals: biochemistry, analytical biochemistry, BBA, biochemical, biophysical research, communications, biochemistry, all that. They're all in mainstream journals and they've got fair amount of citations. Why? Why? Because your senior is with you. All right. You try to wade against the current, it's difficult. But sometimes if you want to be original, you have to be when you are right. So I did that, but I maintained my relation with Lowell. Even after I came back, he was my mentor. He would say, why are you after this? And then I tried to convince him. Then I told you in 1993, when I had this accident, I decided that I'll come back for social work. Then in 2000, I had asked Lowell for permission to work. I wanted to go back. I want to do something good to convince myself that I've justified my scientific training. And in this, I thought, okay, chlorination is not active site. Happy. I wanted to do America. When I had gone there, I was from Kerala. I thought America, I had somewhat leftist leanings at that time. America was not a good country, but I just went to check it out. And then I had kept myself skydiving as one target. I skydived and I tried to find out something new. I found something new, justified my this thing, and came back. And then in 2003, I exhausted all my money, did some independent social work, and then I went back. And then when I went back, that's when I published that chlorination work. Because when I went back, I started working on drug metabolizing enzymes. That's our liver. Very complex enzyme systems, $1 trillion industry. Chloroperoxidase, of course, is a very important enzyme. All that. But then I kept in touch. I could publish it, and Lowell came around at that time. He wrote his lifetime memoir in JBC, Journal of Biological Chemistry, and he wrote that Murali, what he showed was right. And so then onwards, we started collaborating. We published in biochemistry also, and then Danny and we published a paper with him. So the point is, in chloroperoxidase, my works are highly cited and I'm respected. You can see. But other people, they didn't come around. I was fired multiple times in America. Fired. All right. In the land of opportunity. So if you want to do your work, they were not very good. Some people, that appointment time was 3 months probation time, and then after that I gave a talk. I don't think this is active site. Tongue assessment backdated. Fired. Multiple places. So I came back. Danny and Abhinav, we started our own group, and then we had Surjit. Where is Surjit? Surjit was an IIT Guwahati. I was his professor at Shastra. Then where there is a will, there is a way. You want to do things differently. You want to question. You have some people by your side. He then arranged for me, when I was working, to make presentations with other labs. This was taken in 2006. This picture. So what I found in 2006, even now 2024, in drug metabolism, it is still not applied. Drugs are still being optimized without the right theory, without the right approach. last, we will talk about it in the next meeting. Even in recent times, I reached out completely unscrupulous, no moral integrity, no intellectual merit. If all of you are listening, take it. They all know what I'm saying is right. But the slide that I put in front in the initial phase, what Max Planck said. What did Max Planck say? A scientific truth does not get its roots in society because of its merit. Satyam meva jayate. No. You see, the first statement was by Carolyn Wells. What did she say? If it is true, if something is shown as false, it should be discarded. What I have shown is clearly falsity of multiple things. It is still going on. So, after this chloroperoxidase, the system that I worked was with drug metabolism. But to make you understand murburn concept easily and more effectively, in the next session, we will do lactate dehydrogenase and hemoglobin, two other murzyme systems. And I think we have put lactate dehydrogenase as the first one. I think we should go with hemoglobin first, and then come with lactate dehydrogenase. You can start with hemoglobin and then come with lactate dehydrogenase, because lactate dehydrogenase is a more complex murzyme than hemoglobin. Hemoglobin is a simpler murzyme. All right. So here I would like to stop for this session. Has the tea come already? Tea vandircha? Yes. So good. So now I open the session for interactions and questions. Is the idea of murzyme and murburn concept sinking in? Yes. Good. What about you students at the back? Is it sinking in? How does it relate to what you have been studying or what you have studied? How is it? See here, utilization of peroxide. Here I show that peroxide is not deactivating. That he could agree. He had said that it was deactivating, but he could take back his own word, but he could not bring himself to put his name on the electron transfer occurring outside the active site, chlorine transfer occurring outside the active site, because that's a social thing and he's a social entity and he could not. So did you understand what I'm trying to show here? What will keep you going is self-belief. What you believe is good. And that, if you don't go do science. Don't do science. Discard science. After your BTech, BSc, whatever it is, you do something else. Take some other. If you are not interested in science, if you are not interested in curiosity, if you are not interested in doubting, if you are not interested in questioning, don't do science. If there is a spark in you, that can be turned into a flame. If there is no spark, how much ever oil is poured will only dampen your spirit. Do you understand? Yeah, everybody need not be a scientist here. Right? It's not your call. So you need to make this call. You need to understand, you need to ask yourself, am I interested in making products and things like that? Become an engineer. Understand that. Scientists, generally, you need to be, something happens, it catches your attention. Ye kaise ho raha hai? How is it? How can it be? That is what phenomena. That should interest you. If you're a technologist, you make products, processes, do that. Ask yourself, what is it you want to be? That's what the whole process is about. If you're a student, see, please pardon me, majority of, I don't see one or two faculty only, serious senior people. The vast majority of you, like I said, you're not going to become toppers, every one of you. Somebody, you will not be getting to marry Aishwarya Rai or Hrithik Roshan, not the best ones out there either. You will find somebody, you will settle for somebody. Yes or no? Similarly, like you settle for one mate or something like that, similarly you have to find your call in your life as far as your subject is concerned. And you will have to know all the subjects also, but in some subjects you will have to be better than others. That's what you can aspire to be. So the three philosophies that I said, you will see me reiterating: explore, resolve, prioritize. Chance favors the prepared mind. Once you find something that you like, you kind of prepare in that, and then pursuit of excellence is based on what you have and what you know. I had Lowell, I based on him. I had Abhinav, I had Danny, I had Surjit. Surjit was in IIT Guwahati. I knew. I gave him some experiment. Whatever little I had, now I have Amrita, I have my colleagues here. We are trying to base our exertion on that. I have you people. You are the ambassadors. If you believe after this session, murburn, you go out another day after that, my effort is going to be wasted. But if you go talk to your other person, this is the biggest paradigm shift in history of science. In 21st century, we are going to tell the world from Coimbatore what oxygen is doing. Can you imagine that? Can you imagine that? Respiration, photosynthesis, the two processes on which all life forms on planet Earth sustain. So when I put that 1927 Solvay conference, and when I said that this is as important, I was only being humble. A factual statement should have been based on their quantum physics and all that mechanism and all that. This is a quantum effect only, effective charge separation. Electron has to leave. So, all that is ultimately going to be explained in that. But the point is, all that fundamental awareness, and you still are not getting to the real ballpark of how those wonderful scientists have done. So in that, I am actually being an engineer when I try to explain things. But then I've kind of, my group and my collaborators, what we have done is we have founded biological processes in the fundamental concepts of physics, which you will see. We have just shown you some basic experimental observations. Where are we now? We have given you an overview of murburn in the first talk, which Professor Lauren Jakin gave. In the second one, I gave you a very simple experimental way in which active site nahi ho raha hai, it is coming outside the active site, and diffusible species can also give selectivity and specificity. This thing I established. And these two things are, though small, they are very big in terms of the ramifications they bring. Yes. Our life, culture, everything will change. Everything is going to change. Yeah, chaos se chaos tak. That is the journey that we take. But then we know, with that we know. So we have to be very, very careful about the freedoms that we have. Which is why I do not believe in too much freedom to the younger generation. When if you give too much freedom to the younger generation, some of them will go excellent, but the vast majority will go, because I know, I was a youngster myself. All of us were. Alright? So yes, the session is open, and after that we'll have tea. Tea is already here, right? Yes. Those who want to go for tea can go. Those who want to stay back for interactions can stay back. Yeah, my phone please. And please somebody record this please. Please record the interactions. That's very important. Because only then...
Excuse me, sir?
Yes, Yashpal, can you wait? I would like to give precedence to the people who are here. Then we will come to you, Yashpal. Once they go out, I can take you now. Yeah, sure. Thank you.
Sure, sir.
Yeah, sure. Thank you so much. So where's the phone and where's the camera? Yeah, microphone. Yeah. Thank you. Oh, sorry, I didn't see it. Please give it. Yeah.
Yeah,
And excuse me 1 second. When I say interactions with me, it doesn't mean interaction with your butt buddy there. Butt buddy, what I say? The people with whom you... Yeah, no. That's what you do in classrooms. Here you are in a symposium.
You interact with the speaker. Even in your classrooms, if you are doing that, shame on you. That's not something, that's not your purpose. You're not supposed to do that. That's dissipation of your potential. Your potential, you are supposed to spar with the speaker. Enhance your confidence, communication skills. If you are not going to be impressed with what I say, you are not going to be impressed with anything in near future. I don't want to be that negative. In greater future, there will always be something. Because here you can see I'm an achiever. I'm an ordinary man. I'm one like you. From modest backgrounds, if I can do it, not because I was sitting and commenting something with my, I would stand up and I would question my professor. I would say, sir, ye kya hai? I didn't get employed in IIT Madras because of that. My two professors, they said he's too outspoken. I went to the interview in kurta and dhoti. I was supposed to wear a kurta and dhoti today, but sadly my kurta and dhoti I washed and they were not ironable in my house. So I could not. So Stephen, where is Stephen's? He didn't turn up also. So I was going to take his name for being the testimony to this. Because of that kind of aggressive, independent attitude, I could question then, and I wore that. But it had its problem. It will have its problem. I'm saying it is not going to be a rosy, flower-laden path. It will be a difficult path. But then if you want to be a scientist, yes, Albert Sainz-Georgi I put there. There are Apollonians. You can be an Apollonian scientist. But if you want to be a Dionysian, somebody who will be remembered long after you are gone, you will have to take the path not taken often. And taking the path not taken is not chatting with your butt buddies. No. No. Not in my presence. I will not allow it. Anytime you do it, this is my way to show you. This is the only time. Yes, sir.
Thank you, sir. Thank you. That I also like.
Yeah. Because this is the only time. See, I have not had a student for 8 years. So, anytime I get students, that's what I do.
Please.
Yes.
Please.
Yeah.
Sir, I will give two examples. One is the practical, one is scientific base. Another is the pure example which we have to think what scientific base is there. One is the particular ion which bind the site like iron, cyanide and ferrous. One chemical called the tetrahydrocannabinose. I think you must have heard about
cannabinoid. That is the ganja thing from derivative.
It is basically a narcotic drug.
Yes, yes.
But if it is used as a 10⁻²00 dilution, it works as a drug. And now it is US FDA has approved tetrahydrocannabinose at 200 dilution, 10⁻²00 dilution. It cures the leprosy.
Could be.
Cures the leprosy.
Yeah, could be.
So it may be this type of a reaction.
Yes, we are coming to that tomorrow.
Yeah.
The drug metabolism and hormetic dose responses. That's called hormetic.
That is basically a basic principle of homeopathy which I was trying to explain.
So we
another
do not.
Another example is one of the greatest example of the world which people do not know. There was a Russian last emperor called as Tsar.
The Russian emperors have Tsar.
And
generally, they are numbered Tsar.
Last one was Tsar. He is a saint in his government. His name was Rasputin. Rasputin.
Abba Rao Rasputin.
He wanted to kill him, Rasputin. He gave him 1 liter of cyanide. He did not die. He did not die. He digested 1 liter of cyanide.
What cyanide? What concentration?
That is what. At higher concentration, it does not work as a.
No, I would not.
No, I do not agree with it. But it's a
I can tell you.
No, sir. It is proof. It is proof. It is written.
No, sir.
I do not know what science is there.
No. Cyanide, you have 1 kg. You just smell. You're done.
You can go to the Google. I'll give your.
No. Google will look अलग बात है. I am a very open-minded scientist.
It is documented.
But cyanide in...
I don't know. I also do not agree, sir. Sir, I am not...
Yeah, just smell, yeah.
Sir, I am not trying you to agree on that. I am just giving you the...
I understand.
I am giving you the things which have happened on this earth. And people have seen it. It's not very long. Say about 110 years old. Not very long.
No, but
liter of cyanide solution, but if the cyanide concentration was 10 to the power minus 200 or some molar or something, okay, maybe.
So that is being reported, and you can go through Georgi Rasputin. You can put it
I know this story.
Maybe protein complexes were mutated, sir. Maybe protein complexes were mutated in that person.
This is Yashpal from CDLU, Chaudhary Devilal University.
Thank you.
Yes.
Thank you.
Thank you so
Just
much.
I wanted to put
Yes. Any.
And the other thing which I said in between, that homeopathy is totally based on the concentrated 10^22.
Yeah. See, at this juncture, I want to state my official stance on this. Okay. Though we have given the hormetic dose response explanation for the first time, our paper, which he is going to talk about, was published in Dose Response. It is the official journal of American Dose Response Society. They were pretty happy because we were the first person who were giving.
Entire homeopathy is based on.
Yes, sir. Let me come to that. Let me come to that. See, homeopathy, it says that there is a limit to all such kinds of theories. The more diluted, the more potent it becomes. That is a theory of homeopathy. I say, of course, there can be some drug that can be dilute and they can be becoming more potent, but it's not a universal phenomenon. And two, some of the dilutions that they proclaim is...
No, sir.
Please, let me complete.
Sir,
please, one second. No, I'm the speaker here. Please. Let me establish something. When I give you the right, then you speak. Please. That you have to please understand. Now, because this is a very, very important thing that will project my image also. I have to be very careful here. Some of the dilutions which homeopaths claim is, to me, honestly, it's very difficult to accept. I will have to look at the data, but the dilution is phenomenally dilute. Hopelessly phenomenally dilute, which scientists in me, they say that the solution retains the memory of the molecule.
Molecules are not there.
Yes, I find it a little bit of a leap of faith for me as a scientist to accept that. I am still open-minded, but here is, I took that extra initiative from you and I kept it to myself because I would still like to not accept that homeopathy statement on a blank perspective.
No, sometimes that dilution, because of the avocado number, if you find, you will not find a single molecule yet.
That's what I'm saying.
But I'll tell you, different potency, they work in a different disease also. Not only the same medicine works for different.
See, the reason that I said is...
They have a scientific base for it. It's okay, sir. We can discuss on
that's what.
platform.
The point that, see, we believe in certain calculations and certain things that are reproducible and all that. So, when the homeopathic drug works, many drugs work through purely placebo. There's a saying in Malayalam, and there's a story in Malayalam. An old lady goes to a doctor, says, she says, oh, I'm feeling very sick. So the doctor says, grandma, what's your problem? What's your problem? So she says, she says, you do one thing, you keep your stethoscope and just try. No, he does. Now I feel better. Placebo is a genuine thing. It also works. But I'm not negating that. I have not done research in that. My official stance as of now is certain dilutions are phenomenally far to
I have not done any research on it, but I have seen its effect on the disease.
Yeah, I understand. See, I understand your passion.
They are effective, 100%.
Yes, I understand your passion.
Even US government FDA has now approved.
Now I have to take your mic. 1 second. Yes, thank you. So now we'll have to give it to somebody else.
Thank you.
Yes. Thank you. Yes, I understand. I love this passion. This passion. Please put a hand for Unadkarji. He's from Mumbai. We met at Bharatiya Vigyan Sammelan in Ahmedabad, and he has come all the way based on that contact.
22nd of December.
Yes, he remembers that. Yes. So, any questions from students? Yes. I'm happy that nobody has gone for tea. So it shows that there is some. You can go for tea if you want. Yeah.
So
what's your name?
My name is Mohammed.
82. See, people didn't put their name. That's what. I had said that this will happen. I said this will happen. That's why I wanted them to put their name. So I could have gotten your name if that name was put there.
I'm Mohammed Mania.
Mohammed Mania. Yeah. Where are you from, Mohammed?
I'm from Gujarat.
Gujarat. All right.
So
Okay. You're from
same university.
Charusat.
Yeah.
Okay.
So does the evolution of DROs from murzymes affect activation energy? Is there any effect on the bioenergetics?
Oh yeah, sure. Now here you have a radical that's coming out. That radical guy is unhappy. He wants a pair, highly facile. It will work. So that's the whole point, right? So the effective charge separation that occurs, it also requires energy. But then it's a stochastic phenomena, and those things, there is always, at a given heat thermal state, there will always be something that will happen. The root grounding is quantum chemistry and physics for that, to enable that oxygen, that electron separation and all that. So your question is, now the classic theory says that now if two molecules have to react, they have to collide, and now their activation energy barrier is very high. The enzyme brings those two in proximity in a particular orientation and all that, thereby activation energy, whatever the activation energy of the transition state is lower, and so it goes quickly. Now the point here is this bringing together can also be in two different steps. The concerted, the ping pong mechanism can be one step at the enzyme, one step outside or on the enzyme. That's all. So that diffusible species production is the primary role of oxygen, which is what we are going to come to. We work with peroxide here. It's a reduced product of oxygen. All right. So in that reaction also there is oxygen. You cannot avoid. So the oxygen also does that. So when oxygen takes the electron, it can become superoxide, and then azide can also take the electron, give the electron, so it can become a radical. Then the acidyl radical can take further electron from some other thing. So if this is more stable, stability of a intermediate catalyst is also very important. So that is how the reaction rates go better. All right. So when you study a reaction, there are certain things. There is thermodynamics. All right. Thermodynamics doesn't talk about
Thermodynamics and kinetics.
There is kinetics. Then there is general mechanism, structure, function, distribution, and then there is overall probability and Occam's razor. You know what is Occam's razor? You are doing science. If you are doing science, you should know what is Occam's razor. What's Occam's razor? There is a phenomenon. There are two explanations. All right. Now you have one explanation that's complicated, sophisticated, and all that, and one explanation that's simple, straight. Which one is more likely to be right? Simple. Not necessarily always, but most usually it is. Right? That's what is Occam's razor. So anybody else? Yes. Yeah, please give him the phone, microphone.
Okay. So I had a collaboration with Nagaland Central University.
He is Professor Prasad Burra from KL University, Vijayawada.
Yes. So there we observed that curcumin, they are doing curcumin, its importance in
Haldi.
Haldi. Yeah. So when we add more curcumin, the disease was in mouse models. Basically, they were in fruit fly. What is it? More than
Melanogaster.
Melanogaster. Yeah.
Drosophila melanogaster.
Yeah. So they have a experiment, and they did this particular work. And whenever there is a higher concentration above a particular point, the curcumin was creating problems for the walking ability. But only at a lower concentration it was working. Okay. So this observation is similar to what you were about to give a experimental thing or something.
Yeah.
So my molecular aspect, my molecular question is, an enzyme is there, it expects a substrate, right? Now this enzyme is reacting with a substrate and it is giving some products. Now in your case of that experiment, in that case, as the number of substrates are increasing, as the concentration is increasing, why the enzyme is not giving the product it is supposed to give? And when it is reduced, maybe we can give some explanation.
I don't. Now,
So there is some
it is supposed to give. I didn't understand that part of the question, Prasad.
Smaller concentrations. I have stochastic information that these many enzymes will be interacting with these many substrates.
Okay.
But as this as the substrate concentration increases, okay, I can have less number of substrates, so I can say some activity is reduced. But after a certain point, you are telling that it is completely. What did you say? Some technical words you are using.
Minimize.
So yeah, I want to basically understand at higher concentrations why the activity is lost.
Wonderful question. This is the crux of murburn concept. Now you have enzyme. Enzymes makes DRS. DRS is, suppose, let us say, a cation radical or an anion radical, whatever it is. Let us say a cation radical that's stabilized on an anion or on an anion.
Every enzyme releases this DRS.
DRS. Suppose it is releasing. Now, your question very easily I can show you. Now, too much. Suppose this makes. Suppose now. Suppose this is acidyl radical. Suppose let us say some radical is formed or cationic radical. Something is formed. What will happen if you have too many radicals? No, they will collapse together. They will interact more frequently, and if there is less of those, they will be more stabilized. There is also, depending upon the particular concentration of the mixture, they will get stabilized. That stability is what I was talking about when I said there. The stability is very important. Why? Because if you have more, their intermediate, the catalysis that is mediated by that diffusible species, that will go. Now see, what happens is, now in this we have enzymes. I will put that that basic image. Is it not going? It is not on the slideshow. This one. This one. So the oxygen and H2O should come here. Sorry, this one. So now you see here the product formation, and this thing, and the last slide. What happened? Here you see the stoichiometry. If you are looking here, you have multiple products, multiple reactions going on. You are looking at one particular formation, one particular product formation. Now what happens is that the enzyme is going through its catalytic cycle. It is producing a diffusible reactive species, but that gets converted to multiple other things. If it is stable, at a small amount of sustained amount of thing is produced and it is getting stable, it is specifically reacting only with one thing, because there are innate nature. Suppose each. Now I have given there the reaction reasons. That slide was given by Laurent Jakin. The reasons for reactivity is delta G of formation, the partitioning coefficient, and all that. So depending upon where the diffusible reactive species is produced, if it is produced in a lipid phase, it will preferably react or have more affinity with those that are around that. If it is produced in a bulk liquid phase, it will react there. So the idea is, if you have too much of something and the radical is too much, they will have a greater probability of collision and reaction with themselves. So if I find, suppose if I am somebody and I like science a lot, if I like talking about proteins a lot, I find you, Prasad. So, and if there are too many other people, we will rather stick to ourselves, not interact with other people who are not like us. Did you get the analogy?
The analogy I am getting. Actually, at the end of the day, why so many molecules and less number of enzyme molecules? How this
stabilization of the intermediate. That is what. So now see what is happening here. You are looking at enhancement by the radical. This is the one that is, this is the primary catalyst. This is the secondary catalyst. Now this secondary catalyst can also take electron and give electron, and then it can also do that. And we are not monitoring all the products that are formed in the milieu. So when you are looking only at a product of interest, then we are talking that one particular higher concentration is not good. Did you understand what I'm saying?
If I have understood to some extent, these diffusible reactive species, DRS, so these are not actually happening in the active site. They are acting some other...
See, if it is in the active site, you will say, I call it bros and dros, bound reactive oxygen species and diffusible reactive oxygen species.
Achha.
So, see, bound reactive oxygen species is compound 1. The species T. Yeah, that is okay. I think this is what we are here for. Yeah, your tea. Whoever wants tea can get it. Tea and snacks, you go. Please go. So the compound 1, the pi cation radical that we had. No. I will decide. Please. No. Yeah. Please. I have to. Multiple interest. I will have to keep. Yes. This you understand here. Now this is a bound reactive oxygen species.
Yes.
Now here, from here, if the superoxide comes out, that is a diffusible reactive oxygen species. Now there are in the reaction milieu this complex scheme of mechanistic interactions that I have made here. Here, you see here, there are this compound 1, then there are other things also in the milieu.
Yeah.
People were not really tracking them. Did you understand? There is the unavoidable. People just stuck to bros, because that is what gives selectivity and specificity. But then selectivity and specificity, I showed it is very clearly observable even with diffusible reactive oxygen. And in fact, this can be very beautifully applied for many industrial applications. I am not interested in money. In fact, Novartis did approach me. The drug metabolic intermediates, you can easily make it with this. I showed, even we could easily get that, but that doesn't interest. So yeah, anything else? Anybody? The tea you can go and have. Please go and have. Yes, go and have tea and snacks. But it's not good. So whoever wants, don't make sounds, please. Go quietly. Yeah, I am very don't make sounds. Let us have this interaction. Interaction is more important than tea. I had only one ice cream from the morning. If I can go, so can you. So, yeah. Where is the phone? Where is the phone? Microphone. It will get recorded. That's more important. Yes, this should get recorded.
Okay, so...
Don't make sounds there, please. Yes.
Okay, so you said that the DRSs, they have certain specificity until a certain concentration.
They're not... See, at particular DRS, what it does is, it can react with molecule X. It can react with molecule Y. Let me complete. X and Y. Now, its reaction with X will have a particular energy. Its reaction with Y will have a particular energy. If the delta G is more facile with Y, it's a greater probability that it will react with Y. Yeah. So we are trying to minimize the energy. That's the landscape of the reaction.
So the delta G solely determines...
Not solely. It's also, I said, there are spin rules, then there are availability of certain things, proton availability, then there is partitioning, there are multiple parameters. See, your ability to dribble a ball and go to a particular place is dependent upon your skills, the number of people around, the ball, a lot of things. You have to take, for understanding a mechanism, you cannot just say, this is it and that's it. You have to see all the level parameters. Yes.
Enzymes, they work multiple
Give him.
Enzymes, they work multiple times, like to
Yes.
produce a particular.
That's the definition of an enzyme.
Yeah.
Enzyme does not get consumed in the reaction, does not. Fundamentally, you should all know, enzyme does not change the state of equilibrium. Enzyme only allows the achievement of equilibrium. This is a fundamental error which you will see from lactate dehydrogenase. Beautiful example. Enzyme allows the attainment of equilibrium. It does not change the position of the equilibrium. This fundamental aspect has been established by the great scientists earlier.
But at some point of time, it loses its potency and it has to be replaced.
Yes, that is because sometimes what happens is, if it is a not very energetically strained thing, like suppose if I do this, if I just keep walking, not much changing. But if the interactive species that are produced or the contortions that happen, if it is going through some changes, like all other things, like our body, it will also have its problem. Yes. Anybody? Anything? You should use this opportunity to speak, and that will build your confidence. That's what it is about. Yeah.
So, sir, how you are selecting these enzymes? Means on which basis? Firstly, you got this chloroperoxidase.
Yes.
Then you got hemoglobin. Then lactate dehydrogenase.
Okay, that's a very good question. So you will get to that. So once I got chloroperoxidase, then I realized, I went to this drug metabolism project where cytochrome P50, that will be tomorrow, first session. So we realized that all these enzymes kind of work like this. The respiratory, photosynthetic, everything works like this. So because that's where oxygen is involved, and the whole thing is just application of that idea. So basically, many of these proteins actually evolved to serve this function rather than the active site kind of a thing. Which, see, what happens is, how does science work? Now you have a box, 1:1:1, a box like that. Now that is the domain of knowledge. So whatever new data comes, if that doesn't fit into that box, what do the scientists do? They make a small cone and they put it in the box and they try to fill the cone. It is, the box does not have the ability, but they try to see it like that. Did you understand what I'm saying? It is like that ant and the circle. It will be seen as artifacts, which what Lowell did to me. He said, it must be an artifact. But later on he saw, we are seeing the drug metabolism, all that. People know when they do some study, they say multiple molecules are formed, metabolites are formed, but they will pretend that is not. Why? Because if they try to accept that, establish that, that means whatever the drug regulation bodies have established as protocols, they cannot put their drug through that policy and they cannot get it out. So for them it is easy if it is Michaelis-Menten mechanism, if it is going like that. Did you understand? So how we, addressing your question, how we get to know something is murzyme or not? We are now we are trying to make a database that Prasad
You will go more into the in silico studies.
Yes, we are now we know basically redox enzyme, a significant amount of redox enzymes, a large amount of other proteins. They need not be redox enzymes also. So murzyme means any enzyme that uses a diffusible reactive species or produces a diffusible reactive species or equilibrates with a reactive species or converts one reactive species to another reactive species.
I want to explain that question. She is working on methyl transferase.
Mm-hmm.
Okay, so then is there a way of telling that methyl transferase is also a murzyme?
Yeah, but does it have a cofactor?
It is having one Rossmann fold, one common fold.
Yeah, does it have a cofactor, metallic cofactor?
Yes, I did not L-methionine.
That is marginal. I'm not sure, but I think it is mostly. Is it known to give other products also?
Only one.
So
yes.
yeah, S adenosine methionine. Yes, it has selenium, na? It has. It has selenium, no? Sulfur only. Transferases. See, ATP phosphate was transferred. So chlorine transfer. But I don't think this is because S-adenosyl methionine.
it doesn't give multiple products. I don't know. I don't know. Only methyl group. I don't know. Does it have a broad range of substrate specificity?
No, it will just transfer methyl group. Means it is having one common Rossmann fold, and that SAM will bind there only, and it will transfer the methyl group.
To only one molecule to another molecule, one specific molecule to another.
It will transfer to the different.
You go ahead if you want to have DNA.
DNA also it will transfer, RNA also it will transfer, protein also it will transfer. But it will transfer.
So I don't know. I can't answer your question now. Yeah, we'll first. Yeah. No, but then the question is good. Question is good. You should understand that I will not be able to answer all your questions. If you have the curiosity, go ahead, do it. I don't know. I have to study that enzyme, maybe.
You have to use different substrate for the enzyme and take the trial.
Yes.
Use some caging
Okay,
agent.
so from methyl transferase, I remembered, we were given an assignment on malate dehydrogenase.
Okay.
And its enzyme evolution.
Malate dehydrogenase has it's a redox enzyme. There is a scope, but malate is so fundamental to the metabolic pathways. It has an evolutionary tree. So there can be a very strict kind of specificity and selectivity also, because if you at a fulcrum, if you introduce too much of options, you will have the life system going haywire. Good. Yeah.
So when we were looking at its evolution, and it came from lactate dehydrogenase. So I was wondering, is it because of certain things that lactate dehydrogenase does that it became specific for malate, the enzyme?
Well, I really don't know, because evolution is something we can just speculate on. There's a, I don't know. I have no clue. Honestly, no clue.
It might be worth working on.
Yeah, I don't know. I don't know. You go ahead. As far as I'm concerned. Yeah, seriously. Anything is worth working on. No, that's what I'm saying. You know there are itni खूबसूरत लड़कियां हैं, इतने खूबसूरत लड़के हैं, but you have to stick to somebody at a given point, and you have to stick to be committed to that. You say, oh, that's good. उसके पीछे, इसके पीछे नहीं. धोबी का कुत्ता ना घर का ना घाट का. Yeah. Go ahead. Yeah.
We have no class for you, sir.
That's okay. Thank you. എത്ര പേരുണ്ടാവും? ഇത് സിംപോസിയാണ്. ഇത് അങ്ങനെ തന്നെ ഉള്ളു. എന്റെ സിംപോസിയ അങ്ങനെ തന്നെ ഞാൻ ചെയ്യുള്ളൂ. ഞാൻ രാവിലെ ഇട്ടിട്ട് ഒരു ഐസ്ക്രീമാ തിന്നുന്നു. സോറി, എന്താ സ്നാക്സ്?